Welcome to Physics 101, Kinematics. This video will explore the fundamental physical quantities and different types of motion in nature, helping you understand how things move around us. Motion is everywhere, from large astronomical objects to tiny subatomic particles. It ranges from simple linear paths to complex patterns, like a butterfly's flight. Our scientific goal is to decode this complexity by first mastering idealized forms of motion, such as linear, circular, and oscillatory motion. Describing position requires a fixed reference point, or, quote, origin. Position is defined by the distance and direction from this point.
Position is described by specifying the distance and direction from that reference point. Motion versus rest.
Distance is the total length of the path traveled and is a scalar quantity. Displacement is the net change in position, the straight line gap between initial and final points. Both are measured in meters, but displacement, unlike distance, requires a specified direction. Let's consider an athlete who runs 100 meters out and 60 meters back. The total distance traveled is 160 meters. However, the final position is 40 meters from the start, so the displacement is 40 meters in the positive direction. Scalars are physical quantities specified only by magnitude, such as distance, speed, mass, and time. Vectors require both magnitude and direction for a complete description. Examples include displacement, velocity, force, and acceleration. In physics, an instant of time is a single, specific reading on a clock. A time interval is the elapsed duration between two specific instants, defining how long a process lasted. Average speed is the total distance traveled divided by the time interval, describing how fast an object moves overall. It is a scalar quantity and provides no information about direction. Average velocity is the rate of change of position with respect to time, measured in meters per second. It equals displacement divided by the time interval. As a vector quantity, its direction is indicated by positive or negative signs. In the example of a swimmer covering 50 meters in 50 seconds and returning to the start, the distance is 50 meters. The displacement is 0. This results in an average speed of 1 meter per second, but an average velocity of 0 meters per second. Uniform motion occurs when an object covers equal distances in equal time intervals, meaning its speed is constant. Non-uniform motion involves unequal distances in equal intervals, which means the object is speeding up or slowing down. Average acceleration is the change in velocity divided by the time interval. It represents how quickly velocity is changing. Its units are meters per second squared. Acceleration is a vector quantity, sharing the same direction as velocity when speeding up and the opposite when slowing down. For a bus speeding up from 10 meters per second to 15 meters per second in 10 seconds, the acceleration is 0.5 meters per second squared. During braking, a negative acceleration of -3 meters per second squared indicates retardation or slowing down. Position time graphs visually represent how position changes over time. A straight line indicates constant velocity, while a curved line indicates accelerated motion. The slope of the line determines the magnitude of the velocity. On a velocity time graph, the slope of the line gives the acceleration of the object. A horizontal line means constant velocity and 0 acceleration. Finally, the area under the graph represents the displacement. The kinematic equations describe motion with constant acceleration. The velocity-time relation, v equals u plus at, connects initial and final velocity, acceleration, and time. Kinematic equations use 5 main variables. Displacement, s, is the change in position. Initial velocity, u, is the speed at the start. And final velocity, v, is the speed at the end. Acceleration, a, is the steady rate of change in velocity, and t is the time interval. Motion in a plane means movement in 2 dimensions, not a single straight line. Examples include projectile motion, like a kicked ball, and orbital motion, like a satellite. Uniform circular motion, or UCM, is movement in a circular path at a constant speed. Despite the constant speed, the continuous change in direction means the object is constantly accelerating. The applications of kinematics are vital. Knowing how speed relates to braking distance is critical for driving safety. Further, idealized models like UCM help us understand complex astronomical motion, such as planets orbiting the sun.